Hi everyone, I'm Erdem Bıyık. I'm going to talk about how reinforcement learning can help reducing traffic congestion on shared roads. Needless to say, traffic congestion is a huge problem, especially in large cities. Here is a video from the Thanksgiving Day at Los Angeles from a few years ago, and congestion isn't limited to just single events. Our idea is we can use the new capabilities of autonomous vehicles to mitigate this problem. To formalize, we consider a network of parallel roads, with some human drivers who are selfish, taking the quickest route available to them, and with some autonomous vehicles which are altruistic. We then want to understand what equilibria emerge if all users are selfish, or if the autonomous cars are altruistic. And with the presence of altruistic autonomous cars, how can we efficiently route them to decrease the total delay? I'm going to focus on the second question today. To mathematically analyze the network dynamics, we partition each road into several cells. Let's now look at one of these cells. In the case of a single vehicle type, we model the vehicle flow in a cell using the fundamental diagram of traffic. Let's say we have a road cell with B lanes, which is D meters long. Here is a vehicle that's L meters long and is going with a certain speed V bar. There is this rule that drivers must keep some distance corresponding to a certain amount of time with the car in front. So let's say we have this second car with this headway distance. Therefore, each car occupies a certain space on the road that I show with the blue block here. Now the question is, how many of these blue blocks fit into the road? We calculate it using a geometric wave. So as long as there are fewer cars than this, all cars will be able to go with the nominal speed. We can now show this on a density flow plot. Similarly, we can also look at the flow latency plot. Now the next question is, what if there are more cars? We need to shrink the blue blocks. Cars will have to slow down for this. So what's the length of this new blue block? We simply divide the area of the road by the number of cars. We then use this to calculate the new speeds of the vehicle. We can show this on the density flow plot and the flow latency plot. These plots, called the fundamental diagram of traffic, are useful for model development and convergence analysis. We looked at a single vehicle type so far. The autonomous vehicles are different from regular vehicles because they can keep shorter headways thanks to their faster reaction times. Doing the same analysis, these dashed lines show the density flow plots for the autonomous vehicles. Therefore, we will have two different blue blocks on a shared road. Luckily, we only need the average weighted with the fraction of autonomous vehicles, so we can write the critical density in terms of the autonomy level of the road cell. We also need to study how vehicles move from a cell to the next one. For that, we look at the flow which quantifies how many cars transit to the next cell within a time step. It's limited by, first, the demand by the previous cell, second, the capacity of the cell, which quantifies the maximum outflow, and finally, the supply by the next cell. Given these three quantities, the flow from one cell to the next cell will be the minimum of these. With these dynamics, a traffic network is in a Nash equilibrium if no selfish user has any incentive to unilaterally deviate from their route. While I skip the steady-state analysis and theoretical details here, we showed in our paper that best selfish and altruistic equilibria can be computed in a tractable way. To complete our model development, we look at how selfish drivers choose their routes. For that, we use a model from the literature where users learn which route is the fastest over time. So this is the overall optimization we want to solve. Because dynamics are too complicated, even involving other optimizations for the transitions from a queue to the network, we use reinforcement learning to approximately solve it. Specifically, we are using proximal policy optimization. So we have our dynamical system here. We give the state observations to this two hidden layer fully connected neural network, and it gives us the discrete distribution of routing for autonomous vehicles. We then use this to route the next autonomous cars that wait in front of the queue. We did an example study on a 3-road network from Los Angeles. Each road had a bottleneck segment. To make it difficult, we tried allocating a demand that's 95% of the maximum feasible demand. Here I show the results with varying autonomy levels. The solid lines are the reinforcement learning solution. The dashed lines show the theoretical lower bound of the cost. In comparison, we show with the dotted lines what happens when all vehicles select their route selfishly. As you can see, selfish routing causes a linearly increasing cost, meaning a growing queue in the network. The story is similar for 60% autonomy. For lower autonomy, the optimization is in fact infeasible, but we can see that RL routing is able to keep only a marginal difference to the theoretical lower bound, and it's similar for even lower autonomies too. To summarize, we use reinforcement learning to control the routing decisions of autonomous vehicles to help decrease congestion for all users. One thing we have been recently looking at is how the COVID-19 pandemic affected human preferences about routing and how it will affect the recovery of public transportation. We will be presenting this work at ICCPS this year. With that, thank you.